Welcome to AP Calculus Lesson 1.2. Again, I appreciate Mark Sparks for providing this free AP Calculus AB curriculum on Teachers Pay Teachers. And today we're covering 1.2a, understanding limits algebraically. In 1.1, we examined limits numerically by choosing x values increasingly close to what x was approaching and seeing the trend in the white values that came out. And we learned that when talking about limits, whenever we talk about a limit, we want to know what value am I approaching? Not what value do I get, not where am I at, but what am I approaching? What am I getting near? However, we can look at our limits and not always do we have a graph. If we have the function, we can look at that analytically and oftentimes find a more exact limit than what we would get necessarily from analyzing a graph. What we're going to find with this introductory exercise here is the relationship between the value of a function and the limit of a function that we get from its graph. And recall that when we talked about limits in 1.1, we said the limit has nothing to do with the value of the function. The function does not have to exist. It does not have to be defined. It could be a completely different value. If I had an empty point here and a solid point here, and I took the limit as x approached 4, that limit would be -2, despite the fact that f of 4 here equals +2. This would be my limit right here because -2 is the y value that I am approaching regardless of where the function exists. But what we're going to find in 1.2 is a limit principle that will allow us to find the limit of a function from the value of a function or its related value if a function is continuous or in certain other specific situations. So we're going to start by exploring this graph, and just as a good review, let's find the limits from the graph, each of these as x approaches 0, as x approaches 2 from the right, and as x approaches 10. So as x approaches 0, here is my x equals 0 value, and this is a two-sided limit because it does not specify the left or the right. So I'm going to approach this from the left, and I approach a y value of 2. And as I approach it somewhere in the right, approach it from the right, I also get a y value, of -2. So I could say the limit as x approaches a, where a is 0, on this graph is -2. Okay, we can do the same thing with this limit here. The limit as x approaches 2 from the right. So this is my x equals 2, and I can approach that from someplace on the right-hand side. And as I get close to x equals 2, I approach a y value of -4. So my limit from the right, as x approaches 2 from the right, the y value that I approach, that I get close to, is -4. Now glancing briefly at this third one, the limit as x approaches 10. Well, I have a problem here. My graph does not go all the way to 10. I could try constructing this off the side of the graph and kind of figure out, well, I think it'll maybe go about here and about here. And so I could do that, but eventually I'm going to hit a limit. I'm going to hit a point where I would be trying to create a graph that's just really too large to be practical to work with. If this were the limit as x approaches 100, I wouldn't want to try to draw a graph where x goes all the way to 100. So it's very helpful for us to find another way to find a limit without having to draw out the graph. Before we come back to this third one, I'm just going to call this limit 3. Let's revisit these first two limits. And this exercise asks us to find what would the value of the function be using the equation f of x. So this is my f of x function. And we want to evaluate this function for, in this case, x equals 1. So we're just going to evaluate the function. 1/2 absolute value, -2. My x value will go in there. Close my absolute value, -4. And I can plug in that my x value is 0. Doing the math then, -2 times 0 is 0, plus 4 is 4. So I have 1/2 of 4 minus 4 equals 2 minus 4 equals -2. So let's look at this in context, and what do I see about the value of the function and the limit from the graph? I see that they are equal values. -2 and -2 are the same. Is that the case more than once? Simply getting the same answer one time isn't good enough. I could say, well, 2 plus 2 equals 4, and 2 times 2 equals 4, so adding and multiplying are the same thing. And that would be a false conclusion. I would be trying to draw a pattern from too few examples. So I want to check this again in multiple contexts and see, is there a pattern that I can draw, a conclusion that I can draw from multiple checks and not just from one. So we're going to look at this exact same function again, but for the limit as x approaches 2 here. From the right, I don't need to worry about too much right now. We'll come back to that later. Let's just go ahead and evaluate this for x equals 2. So I have 1/2 absolute value, -2, parentheses, plus 4, minus 4. As x approaches 2, 1/2 of -4 plus 4 is 0. 1/2 of 0 is 0, minus 4 equals -4. All right, let's look back at our context, and we find that, yes, again, the value of my function equals the limit from my graph. Based on this, I can then create a hypothesis, form a hypothesis that if I were to evaluate this function for x equals 10, I would also get the same value that I would get as the limit from my graph. So we can go ahead and evaluate that function for x equals 10. Okay, 1/2 okay, 1/2 the absolute value of -2 times 10 plus 4, absolute value closes, minus 4. -2 times 10 is -20, plus 4 is -16. 1/2 the absolute value of -16 minus 4. Absolute value of -16 is +16. 1/2 of 16 minus 4 equals 8 minus 4 equals +4. So my hypothesis is that my limit as x equals 10 would also be 4. And we can kind of do a very basic check. We talked about looking at our graph and saying, what if I were to continue this graph out? And I could see that if I estimated, went out approximately, to x equals 5, 6, 7, 8, 9, 10. And my graph goes up once for each, up one, up another, up a third, up a fourth. And I would see that at x equals 10, my function looks like it's approaching 10, as that approaches y equals 4 here. Okay, now remember, again, in 1.1, we said the value of the function has nothing to do with the limit. And the limit is not dependent on the value of the function. However, when looking at functions algebraically, what we find is that if a function is continuous, if it is continuous and defined, the value of the function will equal the limit. What we find is that if a function is both defined, meaning the value of that function exists, and continuous at a given x value. A limit can be found such that the limit as x approaches a of that function equals the value of that function at a. This is only provided only so long as the function is continuous. Is continuous at x equals a. And for now, that's all we need to get, is that if the function is continuous at that point and defined, then the limit equals the function. For this period, at this point, all we need to realize is that all of our functions are either going to be continuous and defined or undefined, unless it's a piecewise defined function. And we talked about this a little bit. Our piecewise defined function is going to be something along the lines of f of x equals, and it has the bracket, and it'll have multiple functions, maybe 2x plus 1, or 3, or negative 5 plus 2x. And they'll have conditions for each piece of the function, maybe so long as x is less than 3, or for x equals 3, or for x is greater than 3. And when we have these piecewise defined functions, which we'll see in a later page in this lesson, these piecewise defined functions can cause a function to not be defined at one point and to be defined for a different value somewhere else. Right now, as long as we can plug it in and the function's defined, we're going to assume it's continuous. So looking at each of these functions, I'm going to do the first one with you. We're going to take this function 1/2 x squared minus 2x plus 3 and evaluate that as x approaches 3 and find out, well, what is the value of this function at x equals 3? So I evaluate 1/2 squared minus 2 times plus 3. Now I can evaluate that for x equals 3 and plug my 3 in where each of my x's were. Okay, and evaluate this out. 1/2 of 3 squared is 1/2 of 9. 2 times 3 is 6 plus 3. 1/2 of 9 is 9/2. Negative 6 plus 3 is negative 3. If I rewrite that over a common denominator of 2, I multiply the top and bottom by 2 and get 6 over 2. 9 minus 6 equals 3/2. And this is my answer. You could write this, it's the equivalent of 1.5, and that would be fine as well. So I get 3/2 as this limit because I can evaluate the function assuming that these are continuous. Go ahead and take a few moments. You can work these problems on your own faster than I can demonstrate them for you. So I'm going to wait for just a moment. I want you to pause and try evaluating each of these functions. If you're a little rusty on your trig, don't stress over D and E. Just follow along on those with me as well. Same thing if you're a little rusty on your logs, we'll review those together. Take a moment to work these 5 problems. When you're finished, come back, and at first I'll just show you the answers. You can mark which ones you may not have known, the ones you may have made a mistake on, and then jump straight to that problem being worked if you'd like to see an example. All right, you can see the answers to these problems here, and we're going to work through these in order, B, C, D, E, F. Feel free to jump to the next problem that you want to see worked. We're going to start with B. Okay, how do we get to 17/3? I'm going to find the limit by evaluating the function at x equals 3. So I start by writing out my function. 2 times x, my unknown. Evaluate at x equals 3. So where I had x's, I'll now put 3's. multiplying 5 times 3 is 15, plus 2, over 2 times 3 is 6, minus 3. 15 plus 2 is 17, 6 minus 3 is 3, and this gives me my 17/3. All right, and for C, how do we get 1/3? Let's start by taking our function. In order to find our limit, we take our function and evaluate it as x approaches 2. And again, we'll talk about how we treat this from the left here a little bit later. We'll start with our function, the absolute value, my unknown plus 2, minus 1. The minus 1 is outside the radical, but in the numerator of the fraction. In the denominator, I have my unknown plus 1. I evaluate these where I had x. I now place a 2. In the numerator, 2 plus 2 is 4, and the square root of 4 is 2. This whole thing here becomes 2. Minus 1 over 2 plus 1 is 3. 2 minus 1 is 1 over 3. And this is how we get 1/3. Okay, for D, how did we get 0 for our answer? I'm going to find the limit of the function by evaluating the function as theta approaches pi over 2. So I start by rewriting my function, remembering that with our trig functions, there's this understood parentheses here. And 2 times my theta, which is my unknown. Then I'm going to evaluate this where I had theta. Now I'm going to put pi over 2. Okay, pi over 2 times 2, my 2's cancel. This leaves sine of pi. Looking at our unit circles, since this is one of our quadrantal type angles, looking at our unit circle, pi is going to be 180 degrees around. This coordinate is -1, 0 on the unit circle, and these are labeled cosine and sine. So when I'm asked to find the sine of pi is 0, and this is how I get 0. Okay, for E, how do I get -3 over 4 pi? In order to find the limit, I'm going to evaluate the function as at theta equals 2 pi over 3 in order to find the limit as theta approaches 2 pi over 3. So I'll start with writing my function, leaving space for where I'm evaluating. I'm evaluating at 2 pi over 3, so I can add my 2 pi over 3 up here and my 2 pi over 3 up here. Now, I personally like to take complex fractions and immediately turn them into a division. This is cosine 2 pi over 3, my numerator, divided by my denominator, 2 pi over 3. Dividing by a fraction is multiplying times the reciprocal. So I'm going to immediately rewrite this cosine of 2 pi over 3 times 3 over 2 pi. I like dealing with my complex fractions that way. You can deal with them differently. My cosine of 2 pi over 3. Now this is going to be 2 pi over 3 is going to be 1, 2. This is in the second quadrant or the sine quadrant. Cosine will be negative in the sine quadrant, so whatever I'm going to get for cosine 2 pi over 3, the result will be negative. And then that is a 60-degree reference angle. So I want to look at my special triangle that has a 60 or pi over 3 reference angle. This is my pi over 6 angle, short end, radical 3 and 2. And cosine is adjacent over hypotenuse. Here's my pi over 3. My adjacent is 1. My hypotenuse is 2. So I get 1/2, and that's going to be negative, because it's cosine in the sine quadrant, times 3/2 pi. Negative times a positive is negative. 1 times 3 is 3. 2 times 2 pi is 4 pi. Negative 3/4 pi is my answer. All right, how did I get 1/3 for f? To take the limit as x approaches 9, I want to evaluate this log function at x equals 9. So I'm going to start with the function log base 8 of 11 minus my unknown value. That value, that x value, is 9. Log base 8 of 11 minus 9 is 2. So with my log, I'm asking 8 to what power equals 2? 8 to what power equals 2? And I like to do this by rewriting to have the same basis. So how could I rewrite 2 to be 8? Well, 2 in terms of 8, that would be the third root of 8. So I could rewrite this log base 8 of 8 to the 1/3. Then I'm asking 8 to what power equals 8 to the 1/3 power? And the answer is 1/3. All right, so you might say, that's great. I can find a limit by evaluating at the function. Why do I ever need those graphs? The graphs are kind of nice, but I can just plug it in. Why bother with the numerical limits? I can just plug it in. And what we find, this method, this plugging it in, what we call direct substitution, evaluating the limit, evaluating the function of the limit in order to find the limit, is that it just doesn't always work. What if we try this limit and plug in -3? Well, I get -3 squared plus 4 times -3 plus 3 over -3 squared plus 2 times -3 minus 3. When I evaluate this, I get 9 minus 12 plus 3 over 9 minus 6 minus 3. And what this does is give me 0 over 0. And that's a problem. That is 0 divided by 0 is not 1. Anything divided by 0 is undefined. So here's the trick. You're given a problem and it says find the limit, and you go, okay, I'm going to plug it in, and you get 0 over 0 and say it's undefined. And if you quit, then you're wrong, because the function is undefined. F of -3 here is undefined. But the limit is not necessarily undefined. The limit doesn't necessarily fail to exist just because the function is undefined. So this function was undefined, sure, yes. That doesn't mean the limit is also undefined. Let's check these other two functions. I'm going to go ahead and set these up so we can evaluate them very quickly and see what other kinds of situations can I get with these different values. Okay, so I've set up my functions here to be evaluated for these other values. I can evaluate at 1, and I get 1 plus 4 plus 3 over 1 plus 2 minus 3. And this time I get 8 over 0, which is still, my function is undefined. That doesn't mean my limit is undefined, but my function is undefined. F of 1 is undefined. How about as x approaches 1 from the right, I get the same thing. I will get 8 over 0, or f of 1 is undefined. Now, all right, we've said first we're trying to find a limit. We're given a function. We can try plugging what x is approaching into the function, find the value of the function at that point, find f of a, and if it's defined, then that is the value of my limit as well, and that's great. Now we've said direct substitution, finding the value of the function at the point, doesn't always work. Sometimes my function is undefined. Okay, I've hit a wall, my function is undefined, but that does not mean that my limit is also undefined. It does not mean that my limit fails to exist. For each of these three functions and each of these three limits, we can look at this function in this graph on the right. For each of these three limits, we can look at the graph of the function on the right, and graphically we can see that yes, limits do exist. The limit as x approaches -3, here's -3. I approach it from the left, I get a y value of about 1/2. I approach it from the right, I get a y value of about 1/2. I converge on the value of 1/2. How about the limit as x approaches 1 from the left? As x approaches 1 from the left, I find that I am approaching y equals -infinity. Now, that is not a real number, but I'm only finding a one-sided limit, so infinity is an acceptable answer for a one-sided limit. It's only a two-sided limit that must be a real number. What about if I approach 1 from the right? Here's 1 again. As I approach from the right, I approach positive infinity. So I can see here that these limits can exist even if the function is not defined at those points. And we're going to look at 3 different ways to find limits where their functions are not defined. So basically, when we're not dealing with a piecewise defined function, when we're dealing with a simple one-piece function, we have 2 major types of discontinuities. And we talked about these in the previous lesson. We have point discontinuities, where the function is undefined. And then we have asymptotic discontinuities, where we have an asymptote. And maybe my function looks like this. Okay, and this is my point discontinuity. This is my asymptote. And what these look like is my point discontinuity is where I have some factor. Maybe I factor this out and I get 2x plus 3 times x minus 1 over x plus 2 times x minus 1. And for this function, I would have a point discontinuity where my factor in the denominator would cancel. If it would cancel, then I get an equivalent function that I can still evaluate and find a y value. In this case, this discontinuity, this point discontinuity would be at x equals 1. And I could evaluate by plugging 1 into what remained in order to find the limit. With the asymptote, I would say I have an asymptotic discontinuity, or an infinite discontinuity, and this would be at x equals -2. At x equals -2, because when x is -2, it also makes this undefined, but I have no way to cancel it out. So it remains, and that's what gives me these positive and negative limits. So whenever I have a factor in the denominator that will not cancel out, then at that value, as my limit approaches -2, my limit will. So as x approaches -2, my limit will approach either positive infinity or negative infinity. And in a moment, we'll look at how can we determine which is it. Is it approaching positive infinity or is it approaching negative infinity? And I want you to think for a moment and ask, well, how would I tell if I'm maybe approaching this value? Let's say this is -2. If I'm approaching it from the left, what could I do to try to figure out, is my y value somewhere up here going way up, or is it somewhere down here going way down? So let's look at how we find these limits where we have point discontinuities, where we can cancel them out. So our first step is factor the numerator and denominator. We're going to factor the numerator and the denominator. And this is important because that's necessary for us to be able to cancel. That's necessary for us to be able to see what things can I cancel, what things can I not cancel. Then step number 2 is to see if that factor cancels. If the factor will cancel, then we can say that the function had a point discontinuity. It had a point discontinuity. Again, this is referring to that point that will cancel out. This right here. Had a point discontinuity at the place, or we'll say where, the factor equals 0. And again, here, our factor that canceled out, x minus 1, what makes that 0? What makes this function undefined? And when I say, well, what makes this 0, I set that x minus 1 equal to 0 and say, well, then x equals 1. So I have a discontinuity at x equals 1 in this instance. Then step number 3, if I have a factor that did not cancel from the denominator, if a factor did not cancel from the denominator, and that's probably misspelled a little, then I have a non-removable and infinite discontinuity. Function has an infinite or asymptotic discontinuity, again, where the factor equals 0. And this is what we saw in this example on the right. Because I had this x plus 2 that did not cancel, I set x plus 2 equal to 0, and I say, oh, I have an infinite discontinuity at x equals negative 2. This is where I have this infinite or asymptotic discontinuity. Okay, so we can now verify this. We can look at this function, we can factor it, we can cancel. This would be the same. At this point, I'm not changing anything. I'm just taking the limit still as x approaches negative 3, and I'm factoring. Factoring only changes the form. It does not change the value. This factors to x plus 3 times x plus 1 over x plus 3 times x minus 1. And the only things that will cancel here are my x plus 3's, so I can cancel those out. And I can say that my limit as of x plus 3 times x plus 1 over x plus 3 times x minus 1 is going to be equivalent, equal to my limit of x plus 1 over x minus 1. Now my function, if I canceled those out of my function, then I would have a new, similar function, but it would not be equal. For a limit, though, I can cancel, and my limit will still be equal. Now I can do my plug it in, plug it in. Now I can use direct substitution, and I can evaluate this for negative 3. Plug in my negative 3, direct substitute, and evaluate. Negative 3 plus 1 is negative 2. Negative 3 minus 1 is negative 4. Negative 2 divided by negative 4 is 1/2. And if we look back at our graph, when we evaluated this one right up here, we can see that when we took the limit as x approached negative 3, we approached negative 3 here, and we got a y value of 1/2. And we see the same thing down here analytically. Okay, the last part of 1.2a, we're going to talk a little bit more about the vertical asymptote. We looked at our point discontinuity. Now we're going to look at the vertical asymptote. From our knowledge of precalculus, we know that if a rational function has a non-removable infinite discontinuity, we talked about that asymptote graphically, and a vertical asymptote exists. A vertical asymptote. Okay? Since the y values do not approach one specific value from both sides, we said even if it looked like this, even if it did, it still wouldn't be a two-sided limit because they would be approaching a non-real number. But since they don't approach typically the same value from both sides of a vertical asymptote, okay, the two-sided limit, or the limit, does not exist. But we can still determine one-sided limit, the limit from left or the limit from the right. In order to do this, really we're going to bring that numerical approach back in. And I said if we had a function and maybe one side went up at the asymptote and the other side went down at the asymptote, how could we tell as we got close to this value, let's say this is 0, as we got very close to this value, how could we tell whether we were approaching positive infinity or negative infinity? I can look at the function, and we've seen this function before. It factors to x plus 3 times x plus 1 over x plus 3 times x minus 1. And we said, oh, my x plus 3's, they cancel. That's a point discontinuity at x equals negative 3. That's the value that would make, that's the x value that would make the denominator 0. Then I say, well, I have this left, this factor in the denominator. At x equals 1, I have an infinite discontinuity, which means the two-sided limit does not exist, but I can find my left limit, my value from the left, and my right limit, my value on the right. So let's talk about my value from the left. We'll redraw this function as an asymptote at 1, so we can kind of look at just a basic idea of what this would look like. And here's the thing with this function, I don't know. Does it go like this? Or does it go like this? Do I have a limit to positive infinity on the left and a limit to negative infinity on the right, or vice versa? And what I can do is say, well, what if I just got really close to 1? And I said, well, when I get really close to 1 from the left, do I head toward a large number? Or do I head toward a small number? And we do that by checking a value very close to 1 on the left. We plug it into the function, and we can plug it into the simplified form of the function. It doesn't have to be the full form. We can use the simplified function right here, x plus 1 over x minus 1. And I choose a value very close, not 0. 0 isn't really close enough. I want in the decimals. 0.9 is good. You could use 0.99. The advantage to 0.9 is I could do this even if I don't have access to a calculator, and you may well not have access to a calculator for a problem like this. And in fact, I find that I can even estimate this. I don't even need to calculate it out exactly. I can say 0.9 plus 1 over 0.9 minus 1. 0.9 plus 1 is going to give me some positive number, and 0.9 minus 1 is going to give me some negative number, and a positive divided by a negative will be negative. Therefore, I can assume I would get negative infinity. Now, if I actually plug that in, 0.9 plus 1 is 1.9. 0.9 minus 1 is negative 0.1, and I would get negative 19. And remember, when we saw those larger numbers, we said those indicated to us that we were approaching an infinity, and we could look at the side to the sign, and we could look at the sign to determine which one. So we see here that we're approaching negative infinity. Now, don't just assume that since we approach negative infinity from the left, that we will be approaching positive infinity from the right. There are a lot of different types of asymptotes, and depending on our function, we want to make sure we get the correct answer. Don't be in such a hurry that you miss half of the points. So we're going to go ahead and test this. It's pretty quick. We can do it right and do it correctly. We're going to evaluate this from the right. We choose a value just barely greater than 1, 1.1. And we plug that into my simplified function, 1.1 plus 1 over 1.1 minus 1, and say, well, 1.1 plus 1, that's going to give me a positive. And 1.1 minus 1, that's still a little bit positive. So I'm going to get a positive number. I would say that I'm going to approach positive infinity.